Hi, can you hear me?
Yes, we can hear you.
All right, awesome. All right. Okay, so let's see. We are on the 4th week. Welcome. And I believe we have a quiz today, no? Let's see. Week number 4, quiz number 2, creating. Can everybody see the quiz on their modules? Actually, let me just make a quick change. Let's see. Yeah, so everybody can see it? All right. I believe if you click it, it'll ask you for a password. Is that right? Actually, let me just turn that off. All right, you should be able to start it. It says 30 minutes, but you should be done much earlier than that. Can you all online can you start the quiz? Do you see it?
Yes, we can see it, Professor.
Okay. Yeah, no, I turned off the password, so you should be able to start it. The quiz is open book, open notes. No, just the data type. And for data types, use valid SQL data types. No. In a single field, you should only put one word. Yeah, one word per field. Doesn't really matter.
Professor,
Yes.
just a quick question regarding the last question, question number 4. So I can see that that's a self-referential table, but as far as I remember in the homework, the only way to create a self-referential table is to alter after creating it.
No,
No?
there
Okay.
are 2 ways.
Okay, got it. So you can create the self-reference in
Yep.
when creating the table itself.
Yes.
Okay, got it. Okay. Thank you.
Should this be considered as 2 words?
Yes.
Okay.
Mm.
So this is not all okay.
Yeah, so that's not the first word. Yeah, so it's a foreign key. You want to declare a foreign key? So foreign key references, blah blah blah.
Oh, so
There's 2 words. So this one goes here.
but this one is still the full reference.
Mm-hmm. Yeah, it doesn't matter. Capitalization doesn't matter. Yeah.
Foreign key. And then the references.
Yeah.
A dot. We don't have that name is over
I'm sorry.
We don't have that name is over here.
No, you don't need a DB. You don't need the database name.
Writing constraint not mandatory.
No.
Do you think I could have lost a marks because I didn't write null?
No, I don't think so.
When did we get to know the right answer?
I'll show. Yeah, I'll make them available. How many are done? Who's not done? Sorry about that. All right, who's done? Who's not done? Okay. About online. Can I have a show of hands? Who's done?
Hey, Professor. Um,
Yes.
when, how do we see the correct answers? Like, do we have to request it from you?
I will show the correct answer later tomorrow.
All right, thank you.
Okay. All right, let's get going. All right, excellent. Yeah, welcome. It's we're on our fourth week, and so up to this point, we've installed a database. We've learned how to design or represent data in a UML using UML class diagrams, a standard visual representation that allows database folks and non-database folks to communicate with one another, and just by making a few tweaks, we can communicate with different audiences, right? To make sure that everybody's getting what they need. Then we spent about a week talking about how is it that we can actually implement them using SQL create statements and see what can be converted from a conceptual design down to something concrete that we can represent in a relational database. We saw that there are some gaps between what you can represent conceptually and graphically and visually and what you can actually do in a relational model. But nevertheless, we agree that is a much better place to design things in the visual world, in the UML, and that we need to be able to straddle between these two worlds, right? Think and design in the visual world, but then understand what the how that maps to a relational world, right? And be able to go back and forth in our heads or on paper, right? And be able to convert from one place to another. And so this week we're gonna spend some time talking about, once we have the database and we might have data stored in there, how is it that we can retrieve and query the database to be able to answer certain questions, okay? The data is spread over multiple tables. Presumably it's a fully normalized database that we've removed redundancy, we've removed inconsistency. We was making sure that it meets first, second, third normal form, and we make sure that we have no functional dependencies. We only have full functional dependencies, but not non-key dependencies. So it's perfect design. So how do we start using it? So we'll spend this week talking about retrieving data using the select from where command, right? That allows us to answer certain questions, and all those queries are based on actual things that we might want to ask the database, right? Which presumably has been driving the entire design, right? The kinds of questions that folks might want to ask the database drives the whole design, right? Then the creation of the database, and then all those select statements that we will want to answer those questions. So we'll spend some time there. Next week we'll talk about other very common operations such as inserts, updates, and deletes, which we commonly refer to as updating the database. So this week we'll talk about querying the database, right? And next week we'll talk about updating the database. Okay. So also assignment 3 will go out today, and it'll be due a week from today, and it'll be based on querying the database. Being able to answer questions. So we'll give you the database that we asked you to implement last week, right? We'll actually give you that relational database, kind of like the answer to last week's assignment. And then we'll give you a dummy set of data, right? We'll populate the data and then ask you to answer certain questions, right? Find out this, find out that. As always, it'll be split into a, you see me do it, then you try and do it yourself, and then a challenge portion at the end, right? Like all assignments. Okay. So anyway, that's the plan for this week. The quiz, the answers to the quiz, I'll make those available later this evening, maybe tomorrow. There's a couple students that were not able to take it today, so I just want to make sure I don't make that available a little bit too early. Other than that, any questions, concerns? Yes.
I have a question about, kind of relates to the challenge from the company.
Yep.
But it's more like a general sense.
Mhm.
So when we see one of these diagrams, and we logically know that, like, certain tables, like, logically would be restricted, like, how do we know, or how do we, like, assess whether this is probably something I can restrict at the database level, and so I should, like, keep searching for it, or no, this is something I can't restrict at the database level, and so I need to, like, let it go for.
Yeah, actually, we will look at an example of that where trying to solve for inconsistency, or sorry, trying to solve for redundancy if you by normalizing actually breaks another requirement of a constraint, right? And so you either you fix the constraint or you fix the redundancy, right? And the database can't do both. And in that sense, that's going to be a segue into why do we need functional programming, right? And, store procedures and triggers and things like that, right? That the declarative language of SQL is not enough to establish complex rules, right? You might put a constraint that a student can't be in the same section twice, right? That's a constraint. Okay, I make a compound key, primary key, right? But then in that same table, you might have fields that only depend on the section but don't depend on both, right? Okay, well that breaks second normal form, and says, well, but if I break it, then I can't enforce the constraint that a student can roll more than once. But it has to live there, right, for some other constraint, right? And so you're left with a no good option, right? That SQL just doesn't give you the option to do that, and that's a good segue into why we need functional programming, such as store procedures and triggers, where you can actually program the logic, right? And then look at the code, look at the insert that's coming into the database, and then run some logic, right? It says, okay, well, is that student in the same section twice? So you can enforce the constraint without actually making it a compound key, right? So that's where we're going to be going, right? Yeah, you can't enforce everything. There's a limit with just plain old SQL.
I guess I'm always just so used to trying to enforce everything all the time.
Yeah, no. Oftentimes you have more and more we have been moving away from enforcing things at the database level. Like if you look at all these non-relational schemas like Mongo and all these non-relational databases, they try not to enforce anything in the database, right? That it's all at the application level. So they just have it as a storage, just as a storage dump, right? That you can always bring into the database, right? Into the application and do all sorts of enforcements, right? And all sorts of analysis and whatnot, right? Especially if for data that might not even be structured. You don't know the structure a priori, right? So you don't even know what the constraints are, and that you might discover them as you go along. Yes.
Going over like API REST design later on.
Yes. Yeah. Yeah, we will. Yep. Yes. Uh-huh. Yeah, so the Yeah, so SQL, MySQL already supports the data type enum, and several vendors do as well, but it's not universally supported. So the best practice is not to, well, it depends how much a organization has bought into a particular technology stack, right? So an organization might be, all Microsoft, right? So all .NET, and they use all their products and every single feature of their databases and servers, and they're fine with that, right? And now some organizations are more open source, and they might be totally fine with using Python in one project or using Node.js in another, and they just, whatever open source is available there. So some organizations are depends, right? If you are more nimble and are not bought into any one particular technology stack, you try to leave your options open, right? So I might want to swap at some point and leave SQL Server and go to Oracle or MySQL or Node or Mongo, right? That means that you try to be try to use the least as possible any features that are specific to a specific vendor, such as enum. Enum is specific to MySQL or certain vendors. So there are portable ways of implementing the same thing, right? And the way we've used them is using kind of like lookup tables, right? Where you have a list of valid options that are primary keys, and then everybody else uses a foreign key, which essentially accomplishes the same exact functionality, right? You are restricting the value of a particular field to a particular set of valid options, right? Migrating from one database to another vendor, it's more common than you think. It's a huge headache, of going from, oh my goodness, I have all these store procedures that I wrote for that only run on Oracle, and now I have to port that over to whatever. It's a nightmare. So it depends. It depends how the organization has bought into a particular. A lot of big organizations do that. They don't want to even have to deal. They buy a license for a decade, and they have full support from IBM or whoever, and they can they can have somebody online. They can fix their issue right away. So other startups don't have that kind of cash, and so they're much more nimble, and they don't want to do that, right? They don't want to tie down. So it depends. Okay, so let's take a look at what do we have so far. All right, so I figured, did we cover relational algebra? Have we did? Okay. Yeah, so let me finish let's go over real quick. So yeah, as I mentioned, relational algebra was all the theoretical basis behind SQL before there was SQL, right? These folks were thinking of, well, if we had a database, how would we use it, right? And so they were coming up with all the mathematical foundations behind it, and it says, okay, well, we'll think of data as being data sets, right, or sets of data points, where each data point can have certain properties and attributes, and which eventually these sets eventually became tables, and the data points became records. Yes, but even before then, folks were saying, well, what would the operations look like? What could you achieve? So these were the three most common operations that you would do on a set of data points. You like to be able to retrieve data points that might meet a certain criteria. So out of a large data set, retrieve for me only those data points that meet a certain criteria. So I need to provide you with the criteria. I need to provide you with the set, and the set and the select statement would iterate looking for all the data points that meet the criteria, right? Obviously, this became the select, right, in SQL, and the where clause. So the select, the where, and the from are coming straight from this select, right? Then there's project, where the data points might have each data point might have multiple properties, which became fields, right, in a schema. And you might not want all the fields. You might only want a subset of the fields, right? And so this obviously became the field lists in the select clause. When you say select field A, B, C, right? ABC is a projection. Okay. If you say star, then you want all of them. There is no projection. You want all the fields, right? But selecting a subset is referred to as a projection, right? And now a lot of these operations are kind of transparent in SQL, but if you look at other databases in Mongo or in other non-relational databases, Firebase and all these other databases, they actually have a explicit projection operation, right? And you say, well, what's a projection? Oh, it's this. It's selecting what fields you want. Okay. Then sorting is presenting the data points in a particular order, not necessarily reordering the set, right? And putting the set in a particular order, because by definition, sets have no order, right? There is no first data point, right? Same thing. We should think of records in a database not having any particular order. It's only for presentational purposes. That means we might want to sort the result set by last name, by email, by domain, or whatever, right? It's only for our visual consumption. Renaming, being able to either alias or temporarily rename a field or rename a table, right? Because you might need to use a table twice the name, but that is logically not syntax error, right? But you might be able to rename it, right, for temporary operation, or even the a column or field, you might give it a human readable name, right, so that it can be easier to read. Extend is the capability of being able to calculate values on the fly, right? If a data point might have 10 fields, you might want to, on the fly, as you're iterating for each record, you might want to calculate 2 or 3 or 4 additional fields that were not in the original data set. Okay, for instance, we saw the example last week about full name being a field that you would not want to have in the original data set, right? Because it was redundant, right? Because you already have first name and you have last name. But full name is a perfect extension, right? You can extend and calculate full name by just on the fly concatenating the first and the last name, right? And other calculations that you might want to have, right? Where you might want to average things or add things or calculate max min or things about a particular record. Group by is a operation that allows you to treat records that are in the same table, right? Not across table, but in the same table. And you might want to collate records that are somehow related to one another in the same table. Okay, we certainly know that records might be related to one another across tables with foreign key, primary key, right? But also in the same table, you might have records that might have a field that have the same value, right? So we might want to collate or group together those records that have a particular field that have the same value. For instance, you might have sales, right? And part of the a field in the sales might be state, okay? And you might want to say, oh, well, my question might be, which state had the biggest sale, right? Who had a record sale this month, right? So you could create, you could group those records by state, right? So what it'll do is that it'll find all the records that have the same state will go in one bucket, right? And then all the records that are in another state will go in a different bucket, right? So it'll be the Massachusetts bucket, right? And the Connecticut bucket and the Texas bucket, right? Okay. And once these records fall in the buckets, you can say, well, what do you want me to do with those buckets, right? Do you want me to average them out, right? Do you want to sum them up? Do you want to find the min, the max? You can apply some aggregation operations, right, that allow you to collate those values into a single set of results. Make sense? So group by, very, very powerful, that allows you to do that kind of thing. Transcript, okay. Yeah, so all these are single table operations. And there are also operations that include multiple tables, right? Or well, at least 2 tables, right? 2, 3, 4. You're gonna, 3 tables can always be considered reduced into multiple two operations, right? And so anyway, so the first one is called product, and product literally means that you're going to do the cross product multiplication of 2 data sets, right? Where one data set might be ABC and the other one might be 1, 2, 3, right? If you do the cross product, you end up with A1, A2, A3, B1, B2, B3, and then C1, C2, C3, right? Meaning you are considering all possible combinations, right, of all the data points in one set with all the other data points in another set. Yes, right. And it's called a product, and so this operation represents the nature of when you have two data sets, right, or two records. I'm sorry, 2 tables with multiple records, and usually we have records in one of the tables is somehow related to other records in the other table. Yes, and usually we know the relationship because some records in one table have foreign keys to records in the other table. Yes, we know that they're related. Okay, but not all records are related to all the records in the other table. Yes, you might have students over here, you might have departments in another one, and you might have a few thousand students here related to a single department, and you might have another 2,000 record as students referencing a single department, another department. Make sense? But how would we find out which students are with which department? Now, the way we would have to think about it is that, well, you would have to iterate, right, over one of the tables and look at the foreign key in each one of the records and compare it against the primary key in the other table. Make sense? Right. That means that there's a loop that iterates over one of the tables, and there's another inner loop that iterates over the other table. Right. And as you iterate over one, you say, okay, well, is this foreign key equal to that primary key? No. Is this foreign key equal to that primary key? No. Is this foreign key equal to that primary key? Yes. I'm going to grab that one. Okay. And you continue, right? You just loop all the way through, right? And then you start over and you advance the other pointer, right? And then you loop the whole thing. So basically you end up with a nested loop where you're considering all possible combinations. Okay. Right. So basically you are considering all cross product possibilities. Yes. First, you consider all of them. After you consider all of them, you want to filter. And the filtering is in the if statement that says, is that foreign key equal to that primary key? Yes. Meaning you are considering it, but some of them are you throwing away and some of them you're keeping. Make sense? Right. And that's where join comes in. Right. So first you do the cross product, meaning you have 2 nested loops that are considering all possible combinations, but then you're going to filter. You're only going to keep the ones that make sense, only the ones that whose foreign key is equal to a primary key, right? Which is basically what? A select, right? A select is basically taking a result set, right, and applying a predicate on it, right? So a cross product, so doing this of considering all the possibilities and then applying a predicate is such a common operation, right? Of iterating and then applying a predicate that it has its own name called a join. A join is a cross product followed by a select. Right? You do the cross product, meaning you first calculate all the possible combinations, and then you filter it through a predicate, only keeping the ones that make sense, right? Only the ones whose foreign key is equal to a primary key, and that's a join, right? As we've we'll learn today, or we'll learn about joins today, joining tables and whatnot. Anyway, now there's a whole bunch of types of joins, left join, right join, inner join, blah, blah, blah. We'll talk about some of them as we go. There are other operations, multiple table operations, where you might want to take the output of one data set and the output of another data set, and you just want to join them together. Not join as in cross product, meaning put them in one single set. Okay, you want to calculate the union of both sets. Okay, so and there's also a couple of other types of joins, other outer joins and whatnot. We'll see those. Now, okay, so now these have a standard syntax of using these operations, right? So for instance, the select is the keyword select that takes two arguments. One is the input data set, right? In this case, might be a student, right? Or the set of all the students, comma, the predicate, right? Is I only want the students whose graduating year is 2004, okay? That means that I am filtering vertically, right? If I think of records, right, as a stack of rows, and there's thousands of records, well, I might not want all of them, so I filter them by this predicate. So out of those 40,000 students, I might end up with just 2,000 that graduated in 2004. So yeah, so that's the select. And now formally, there's a mathematical notation, right, where you have the symbol sigma, right, with the predicate underneath. Okay, so this was kind of like what folks were thinking about, thinking about mathematically, what could they prove? Ideally, what they wanted to be able to answer is there, can I guarantee that the answers that the database is going to give me, it's not going to cause redundancies, that if I ask it this way, it gives me one answer, but if I ask it some other way, it's going to give me a different answer, right? What are their mathematical proofs, right, that I can guarantee certain answers, right? So that's why folks early on, what they were trying to use all this mathematical rigor, right, to what eventually became databases. Yes. So anyway, you should feel familiar with the syntax, right? You should feel familiar and comfortable with using either syntax. So here's just a couple of examples on doing a select on the student and a predicate that has a Boolean expression of two predicates, your graduation year 2004 and major ID 10, right? Which is somewhat as we'll see in a minute, right? It's somewhat the kind of like the combination of two select statements, one where the output of one could be fed into the input of the other, right? The AND operator, right, could be rewritten in such a way that you first calculate one, and the select graduation 2004, the output of that could be the input of a subsequent select statement, right, that filters by major ID 10, right? And there would be equivalent. Yeah, exactly. So here's the example where the output of doing first the select student graduation year 2004, that becomes the input of a outer select statement, right, where major ID is 10 and whatnot, right? Also notice this this notation that we're following here, where we are assigning the output of a select of this query to a symbol, right, or a variable Q1, Q2, Q3. And this was very common in that notation. Eventually, this became in SQL views, right, being able to name your queries so that you can then use them as input into other queries, right? That allows you to create ever more complex queries, starting with small queries that you can then use those outputs to create even bigger queries, right? Very much like you would use programming languages to create functions and whatnot, so you can reuse and create ever more complex functions. We can also think of these queries graphically, right? That starting off with the input data set, in this case a student, flowing the data kind of flowing upwards, where you first have the first select statement filtering by the graduation year, and that is being fed into another select statement that filters by major ID. Okay. So you should feel comfortable thinking about this in the three ways that we can represent them, right? Using the symbolic sigma, right? Mathematical notation, or kind of the function notation, or graphically. There's also projection. Projection the formal notation is to use pi, pi, where you take the data set as an input, and then the fields that you want to keep, right? You want to filter out all the fields. You only want to keep those two, right? So there it is, right? So, or in a function notation, right? The input and the fields that you want in curly brackets. Now you can combine these. You can combine selects and projects, where you first have a select that filters vertically, that says, okay, well, these are only the subset records that I want, and then projection kind of filters horizontally, right? Which fields do I want, right? Out of the 20 fields, I might only want 3 of them, right? Now you have to be careful that the output of one is a valid input of the other, right? Notice that if you do a projection first and you filter out certain fields, right, that an outer select might need, right, then you might end up with an empty set, okay? Where for instance, in this case, yeah, you first filter out the students, and out of the 10 fields, you only keep the student name, and so now you have a single column, right? But then that is then fed into an outer select statement whose predicate is on a field that doesn't exist anymore, right? You kind of filter it out; it's gone. Right? So you have to be careful, right? That if you need at the end to filter out use a predicate that depends on a field, that you leave the field in the project so that you can actually use it, right? So yeah, you have to make sure that right, that the query makes sense, right? You're not going to end up with the empty set. Sorting, there's a syntax for sorting. You give it the sort function, the data set. It could be a select statement. It could be a project, right? That generates a list of records, and then how you want to sort it. Okay. Renaming allows you to take an input set of records and rename the field you want, right? So student name, you might want to rename it to be CS majors, right? This will come very, very handy later on to do self joins, right? Like for instance, where you have a foreign key referencing the primary key in the same table, right? To deal with those kinds of tables, oftentimes you need these renames, right? There will be no way to interact with these self-referencing tables if you did not have the rename operation. Extend allows you to calculate on the fly values. So for instance, the student might have the graduation year, right? But then we would like to be able to calculate whether this person is an alumni, right? Whether they've been graduating already, and that would be the result of looking what years today and when were they what graduating year did they graduate on, right? So if it's later, then yes, they're alumni. Otherwise, they're still in school, right? So we can calculate that as an additional field, alumni, and put alumni next to the results, okay? And we can calculate that on the fly by doing a subtraction, subtract current year minus graduating year, right? And if it's positive, then we output alumni. Otherwise, we don't, right? So it's that calculation, we can call it, a new field. We call it alumni, right? Or like we're doing here, we're calculating the graduating class, right? Are you the first graduating class, the second, the third? What graduating class are you? And that's calculated by the current year minus whenever the college was founded, right? So if you graduated 4 years later, you were the first graduating class, right? Yeah, group by allows us to create these buckets, right? These buckets where the values of the field might be the same, right? And we want to consider them as a single group, right? I want to know all the orders that came from the Northeast, right? Or orders that came from the Southwest, right? And so presumably they would be a field with the region, right? And so I can group them together and say, okay, I'll put all those Southwest in this group and the Northeast in this group and the mid, in another group. And then you can apply all sorts of aggregate functions that allows you to calculate maybe the average or the minimum or the maximum or how many you want to count, how many are there, right? So aggregate functions allow you to collapse or collate the 30, 40, 50 records into a single value, right? They get collated, right? So for instance, you might want to, collate the students, right, by their major, right? What college are they in, right? So that means I would create a bucket per college, right? And then I would have maybe 1,000 students in one bucket, 2,000 students in another bucket, right? And then once they're in the bucket, I can ask, well, okay, well, in that bucket, what is the least and most value for the graduating year? So I can know like a range of people, how they're graduating, right? And then I can ask her about each bucket, right? So this calculates the minimum graduating year and the maximum graduating year of all the students per college. And oftentimes when you get questions like that, like in the assignment for this week, you ask, calculate blah blah blah, the many projects, yada yada, per task or per employee or per whenever you see that, that's a clear indication that they're asking you to group this, right? To create these groupings, right? And then aggregate some and apply some aggregation. So here's an example of students and the colleges that they belong to. If you group them by the college, you end up with, we have 3 students in one college, 4 in another, and 2 in college number 30, right? And we were asking about the minimum and the maximum graduating year, right? So it looks like those two, 2004 being the minimum and 2005 being the maximum for that group, right? And then over here we have 2001 being the minimum, right? And 2005 being the maximum, and here 2003 and 2004. Okay, so group by would allow you to implement that, right? So you would end up with something like this: 3 groups, right? Because there are 3 colleges, and the minimum and the maximum that we calculated from using the min and max operation. You can also group by multiple fields, right? That meaning that the combination, right? The combination of the 2 fields create the group, right? So I might say by state and by region, right? And that creates a group. Okay, and so all the ones that are in the Northeast and Massachusetts, that makes one group. Well, that would just be the group. That would be just the region, right? Otherwise, anyway. So in this case, we're taking the combination of major and year. It makes it a group, right? So in this case, here when we were grouping only by major ID, there's 3 groups. Yes. But if we're grouping by major ID combined with graduation year, then the first 2 records is one group. The second, 2005 and 10, that's another group with a single element. And then 2004, 20 and 2005, 20, those makes 2 different distinct groups with 1 element each. Yes. And then 2001 and 20, that makes a single group with 2 records in it, right? And then we have 2 distinct groups with a combination 2003 and 30 and 2004, 30. That's another bucket each. Yes. Once you have them in each bucket, you can ask, okay, well, count how many are in each bucket, right? Well, there's 1, 1, 2, 1, 1, 1, 2, right? So that's how many buckets we have, which it's exactly what we have here, right? Combination of 10, 2004, there's 2 there. 10, 2005, there's only 1. And we are using count as the aggregate, right? The aggregation function. There's a whole bunch of aggregation functions. There's count, min, max, average, sum, right? There's tons of functions that aggregate and collate the values, okay? Now, one thing to understand is that as you collate, as you apply these aggregate functions, right? The original records are gone, right? Notice that once I collate, right, and this collapses into a single thing, right? In this case is a count. How many? This collapses into the value 2. Well, I lost the student information, right? And I lost the student ID. Yes? Imagine these were 10 records collapsed into a single thing. What happened with the 10 IDs or the 10 student names? Where do they go? Right? They don't participate in the collate or the aggregate right? Only the things that are being aggregated, such as the count, right? That makes it into the output, right? Also, what makes it into the output is the fields that you're grouping by, right? Because these two, right, collapse into single value, which makes sense, 2001, and this collapse into a single value, That makes sense, right? But then it would make no sense that Kim and Pat somehow would collapse into a single what? A concatenation of the names. That makes no sense, right? That makes sense. Yes. So yeah, so that limitation we have to keep in mind, right? That the results of the group by, right, are the fields that you grouped by and the aggregates that you ran, right? But none of the other fields make it into the results. Yes.
The column, the count of SIDs, that just depends. Does that just get populated based on what the function is?
Yeah, right. The default is the yeah, and that's where rename would come in, right? Rename would allow you to say no, don't use that. Use some other name, right? And in SQL, the syntax is using the keyword as that says, okay, well, use this name for the field as opposed to your default weird name. Yeah, so here's just an example of calculating that kind of thing. A couple other things. What if you don't provide the columns by which you're grouping, right? Then that means that the group by interprets that the entire data set as if it were a single group, right? They're all, and so now what do you want to do? How do you want to collate that, right? And it might make, so the collation might make sense or not, right? I guess you could do the minimum maximum of the graduation year. That makes sense, right? I want to know what's who's the oldest or newest student that is graduating this throughout the college. That could be a question, right? Yeah, well, minimum graduation year or count. I want to say, well, how many students are there, right? That makes sense as well. Or you can make it do the average graduating year, right? So you want to know more or less when people are graduating. Or now there are depending on if you don't provide fields that you're grouping by and you are considering the entire table or data set as a single group, right? Then if you do a count, okay, depending on the field that you're counting, right, you might get different values, right? The default is to treat each value as its own independent thing, right? Even if you have values that repeat, right, they're considered to be unique, right? Unless you use a version of distinct, right? You have two versions, right? You might not want to count repeating values, right? So if you have a lot of people living in Lowell or Boston or Dracut, right, and you're having them in different groups, you might want to skip over those repetitions, right? If you want to guarantee that you have uniqueness, typically we count on fields that we know are unique. For instance, you count on a primary key. You know that's going to be unique. Whereas if you count on a foreign key, like we're doing here, you're pretty much guaranteed that you will have repetitions, right? So you might want to treat them as if it were their individual records, right? Or you might say, well, no, I only want to count once, the major ID only once, not multiple times, because I know it's in a foreign key. I'm going to have lots and lots of repetitions. Yes, so you might, depends what is that you're trying to calculate. Also make sure that that you don't choose a field that, well, depending what you're trying to do, it might be that if a field allows nulls, meaning that it's not a required field, counts, when you do a count aggregation, you might get values that you weren't expecting, right? That you do the count as well. That count is pretty low. And why might that be? I mean, I remember being 30,000 records in there. I'm only getting 10,000. What happened? In most cases, might be that you're counting on a field that will have lots and lots of nulls in it, right? that you allowed it to be not you allowed it to be null, right? So oftentimes when we count, usually we deliberately count on the primary key, something that we can guarantee not to be null, right? Or on a field that we know that was required when it was inserted in the database, right? Maybe the email was required or something, right? Or the password is required or username. So you can count on those, right? But not on first name, last name, who might be null because folks have not completed their registration or something, right? Now you can combine outputs of one query as the input of other queries that we mentioned earlier, right? Where you might, for instance, you can make ever more complex queries by starting small, right? Being able to answer small questions, but the answers to those questions can then be used as input to other bigger questions, right? So you have the question here of, who had the most A's? Which section in the university had the most A's, right? So, well, okay, well, we need to find those sections that had A's, and then we have to count them by section, and then we have to, somehow find which is the maximum number, right? So like, looks like there's a lot of grouping there, a lot of aggregations that are going to happen, right? So we can start with something simple as saying, well, find me all the enrollments that there was a grade of A, right? Because that'll give me a reference to the section and a reference to the student. Yes, right? So that means that I can now create a bucket, right, and find all the records. Well, no buckets yet, just the records of all the enrollments, right, where somebody got an A. Right? Once I've identified this subset of enrollments, out of 40,000, I might end up with 10,000, right, or 5,000 enrollments that had an A, right? Some student that was enrolled in some section got an A in that section. Yes. So yeah, that's query number 18. Now we can use query number 18 to go a little further and says, okay, well, what if I group that by the section ID, right? Meaning that I'm going to create for each section, I'm going to create a bucket, right? And it says, okay, well, all the enrollments that were in section 1, 2, 3, I'm going to put it in that bucket over there, right? And all the enrollments that were in section 2, 3, 4, I'll put them in this one, right? And then 3, 4, 5, 4, 5, 6, and so on and so forth. So I end up with, I don't know, 20 different buckets, right? With 10 students in one, you have 3 students in another, and so on and so forth, right? So now you have all these buckets, and that's what the group by in Q819 does, right? Creates all these buckets. Yes. Once they're in this bucket, we're aggregating the buckets, right? We're aggregating the buckets, saying count the primary keys of the enrollments, right? So now that bucket that had 10 students collapses into a single value of 10, right? And then the second one collapses into a single value of 3, and so on and so forth, right? So you end up with a result of the section ID, right? The grouping field, and then the aggregate of how many are there, how many A's are there in that bucket. Yes. So you end up with, say, something like this, right? In section 13, there was just 1 A. In section 53, there were 2 A's. Okay, makes sense. Now this could be the input to a bigger question where we just want to know the maximum. We want to know the maximum, right? So we could use this as a single set, right? And then collapse this, right? Or collate or aggregate this and apply the maximum. The value is 2. You end up with the 2. Okay? But notice that we didn't group by any fields, right? And notice that going from the original query here, which we had enrollment ID and student and section and the grade, all the fields in the enrollment, went from here to here. Because we aggregated by section ID, kind of from here to here, we kind of lost all the other fields. We lost the enrollment ID, we lost the student ID. It's no longer in the output. See that? Only the aggregate field, section ID, and the aggregate, right? We don't even have the grades, which makes no sense because we know they're all A's, right? Okay, that's why they're in here. But my point is that they're no longer accessible here, right? And I'm trying to make a point. Okay, same thing when we aggregate here, right? We kind of lose the section ID when we come here. It says, okay, well, maximum is 2. But going from here to here, we lost the count ID because we just got the maximum, and we lost the section ID. Right? We don't have it in this output. So for instance, here you could not answer the question, which section got that 2? Okay, there's no way for you to put here, comma, section ID 53, right? Because it was lost in the aggregation, right? And every time you do an aggregate and go from one, from input into the aggregate, you lose all the fields by which you're not aggregating, right? Or the ones that you're grouping. Okay, since here we're not grouping by section ID, it's not here, right? So that's one question. So, well, how is it that we can answer, okay, which section got that 2, right? There's no easy answer here, right? A hack way of answering this is to join these two. Do a join where the maximum is equal to the count, right? And then the join, then you can ask in that join which section it is, and it gives you 53. Right? But that's a little bit of a hack, right? So we'll see that that's the result of how group by is calculated, right? It's calculated after the where clause, right? It's calculated after the where clause, meaning identifying all the records, but before the projection, right? And because it's calculated in that particular order, right? You lose all that information. We'll see that in a minute, right? And being a limitation of what can you do with what group by, right? And we need to be aware of these limitations. Yeah, so this is just graphical representation of the same thing: enrollment, you're filtering A's, then group by and whatnot. Okay, and notice that we're always doing this, right? We're naming these, right? We're naming these so that we can then use them in the tablet, or you can combine them using just a plain old, the output of one into the other, right? So here's that there's a select whose output is the feeds into the group by, whose output feeds into a group by. See that? As opposed to naming them. We'll see later on that in SQL you could do the same thing. You can have inline views, right, where you can have a select statement be inside, right, and an inner select statement could be the output of a bigger select statement, which could be the output of a bigger select statement. And we'll see how to do that in a minute. All right, joining table. So let's do that on SQL. Let's move on to SQL. Being recorded. Okay. All right, so let's talk about SQL. Right. So out of all this theoretical discussion on relational algebra, eventually came SQL. So SQL is kind of like a dumbed down English, pseudo English version that folks were, when we were designing SQL, they were thinking, well, what is the simplest way that we can make it for folks to actually use this, right? So they thought of something that could be read in plain English, right? And, as opposed to thinking about functions that you assign to variables to, right? That was too formal. Yes. So they were looking for something that was informal enough that folks could actually read it in plain English. So the most basic command that we're going to be using throughout is the select statement, right? That has the following portions. You have the the select clause that is it's kind of your projection, right? It's kind of a combination of projection and select. So you're selecting, you're choosing what fields are being projected. You're just listing what the input data set are in the from clause. It could be a single table, it could be multiple tables. And if it's a multiple tables, then that's a product, right? If it's just one, there's just one single set. But if it's 2, 3, 4, then that's a cross product amongst all tables. Yes. And then you have a where clause where you have the predicate, right? Or complex predicate, with all sorts of Boolean expressions that allow you to filter which ones you want and which ones you don't. Basically you are, visiting a whole bunch of tables where you have your data that is spread over, and then you're collating that into a single result set, right? Where the predicate is true, right? We are going to be using the same database that we've been using for the last couple of weeks, right? So here's an example of doing a select student name, student graduating year from student, right? Notice that, we're listing the fields, student name and graduation year, and we are prepending in front of each field the name of the table, right? Student. Notice here, because we call that in the student dot, we call it the prefix, right? We're prefixing each field. That's optional. If there's no ambiguity on which table are you talking about, then the prefix is optional, right? You don't have to say student. If the only table that you're talking about is student, then it's obviously just student, right? So you can leave it out. Only when it's ambiguous, then you need to put the name of the table in front of it. Make sense? Okay. You can also use aliases where here's the use of rename. Rename allows you to rename a table, rename a field, create new fields, right? So rename here is we are renaming the table to an alias S, right? It might be too long or too complex, or it might be some whatever, and then you can use that in the rest of the query. Yeah, so we're using just S here, your S.name, S.graduation year. Okay. In particular, it'll be important when we get to self-joins, right? The point of being able to rename a table, especially if the table has exactly the same name. Yeah, so if there's no ambiguity, you can leave out the prefix altogether. If you want all the fields, you can say star, right? So there's no projection. But if you list all of the fields you want, that's a projection. You're saying you want only a subset. Here's an example where you have a department and employee. If the fields are not the same, like for instance, there's employee name and department D name, right? Since there is no ambiguity on the word or property name, because one starts with D and the other one doesn't, then there's no need to put the prefix in front, right? D name is clearly from department and name is clearly from employee, right? But they could have the fields called the same, both names and name. Yes. In that case, you would be required to put the prefix in front, so to disambiguate, right? Here's a couple of examples. We're selecting all the records from persons, so it returns the entire table, or we can do a projection where we only retrieve just the last name and first name, right? If your results might have multiple copies of the same result over and over and over, you can use the optional distinct keyword in front of it, right? And you would say, okay, well, I don't want Lowell to display more than once, right? Now, distinct makes the query significantly slower, right? Because now instead of just coming up with all the results that come in, every result has to be compared against all the results that I've given you so far, right? If it's already in that list, I need to skip it. Right? So that means that there's two nested loops: the loop that is already going through your result set, plus the outer for loop that is iterating over the data set, right? Data types, they're obviously the most common data types, the numeric, integers, floats, varchars, doubles, dates, right? Now each vendor also provides all sorts of functions to do all sorts of arithmetic operations on your data set. All the operations that you might expect for string manipulation, for converting to lowercase, uppercase, trimming, removing extra spaces, tabs, substring, anything you would expect with any advanced programming language. You can do also concatenate two strings. You can do pattern matching with using the like operator for using where you have underscores and percentage to match multiple characters or single characters. And we'll see examples of these. So let's look at the example for like operator, right? Allows you to do regular expression pattern matching, right? Where For instance, the string Einstein could be matched with the regular expression where it starts with a single character followed by a character I, and then any number of characters that follow that ends with an I and then a single character. So that matches Einstein. It also matches these over here, right? It matches anything like this, anything that has an I or not. Okay. So here's an example of using like, you know, in a where clause, and so wherever the column name is going to be to compare it against that pattern, right? If it matches that pattern, then it will be retrieved from the record from the records. Yes. Okay. So here's an example that we're retrieving the persons where the city starts with LO followed by anything, right? And it's case insensitive. So Lowell, even though it's capital L, it matches anyway. Dates, the databases have really strong support for date operations. You can do, yes. Yeah, it's very expensive. Yeah, so if you do pattern matching, ideally the start of the string is fairly long, and you're only doing pattern matching like at the end of the string, right? So that you can quickly filter out strings that don't match, right? And you're just matching on like the ending, the ing or that ends with, right? Otherwise, they become very, very expensive. Yep. Yep. Yes. Ideally, yeah, exactly. Yep. Right, because as we'll see later on, like, between, in, all these are very, very expensive operations that indicate that you have to not only are you iterating or vertically over the result over the records, you're also iterating within the record, right? So something that might have been linear in performance, it actually becomes quadratic. It becomes and it also might be uneven as well, right? You could have clustering of certain data that it's much more expensive certain records than others. Yeah. Yeah. So very strong support for all sorts of data operations. There is a standard format, which is 4 characters for year, dash 2 characters for month, and 2 for day. Although different vendors will have additional formats to support multiple regions, European region, the Far East or Middle East, and other cultures, and all sorts of operations that allow you to do date calculations. How many months are there between 2 dates? How many weeks? How many whatnot? Right. Also, and it also allows you to add different intervals. How much is this date plus 5 days? Also, a lot of vendors, especially Microsoft or Oracle, have strong support for localities, or like they'll know what the holidays are for a particular region, right? So that you can calculate business days, and you can calculate all sorts of really powerful queries about that particular locale or regionality. And there's also a couple of there's current date, which is a global variable that gives you the local timestamp. Extract allows you to break down date as in its parts. So you can extract the month, the day, the year. So you can use it in calculations. You can do additional and add intervals or subtract 2 dates to give you an interval. Very, very powerful. Again, each vendor has its own set of standard that are supported. They all support the standard YYY, month, day, but they might go beyond and support other standards that are not that are particular to that vendor. These are just a sample of the functions that are available in each one of the vendors. They more or less do the same thing, right? But also was useful to take a look at the documentation for each one of these. Now, current date, extract, date add. You can add, subtract, difference. Here's some from SQL Server. they more or less is, so date add in MySQL has an underscore, but SQL Server does not. Right? So just make sure you read the instructions, and code that you write for one might not be for the other. Here's just an example on support from SQL Server for date formatting, that you can convert it into a varchar, and then you can provide all sorts of codes that tells you how it converts it into a different format, right? Whether you want European format, or you want military format, a 24-hour or 12-hour AM PM format. So all sorts of formatting options that they give you. Anyway, so let's look at the select statement. So here's an example of a select statement, using a lot of the features that we described earlier in relational algebra, right? In relational algebra, we said that you have rename, right? You have extensions, right? So here's an example of using a couple of those features, right? So what we're going to do is that we're going to retrieve from student table, and the student table has the graduating year, the name of the student, the IDs, the major, right, where they're graduating. So what we're going to do is that if you just say select star from students, well, that's easy, right? That just gives you the entire table of students, right? All 9 students in our database, right? With all the 5 fields for it, right? The student ID, name, graduating year, and the major ID, right? That's it. Okay. Now to that S star that gives you those 4 fields, right? With the 9 records, we're gonna calculate we're gonna extend this. We're gonna add 2 fields. Okay. One of them is going to calculate which graduating class you are, right? Based on when are you graduating, right? And based on the current date. Okay. And the other one, we're just going to hard code, right, a college name, right? Now this is only for the result set, right? This only goes out to the result set. It's not modifying in any way the original table. Okay, whenever you do a select statement, right, it's retrieving that data, it's massaging it, right, and then it's displaying it for you, right? And you display it, and you're good. Now you could use that output for your eyes only as an input for additional queries. Yes, but all those are always just for output, right? For you're trying to answer some question or generate some data for your own purpose that you're going to maybe export in Excel and do something, right? Or generate some kind of report. Okay. And at no time are we using this to then update somehow the original data, although we can. We'll see that a little later when we look at insert next week. Okay. But up to this point, this is only for output and displaying data for our visual consumption. Yes. Anyway, so yeah, so we're adding these 2 fields, not to the same table. The table stays the same. We're not modifying the table. We're just generating these 2 fields on the fly. Right. One of them is going to be hard coded, a brand new field called college that was not in the original table, and the value is always going to be the same. It's constant. It's always going to be BC, Boston College. Yes. The other field, we're going to on the fly. We're going to create a brand new field called graduating class, right? And on the fly, we're calculating the difference between your graduating year and how far you're in from the when the college was founded. Okay, let's do another one. So this is for instance an example of what that might look like. Let's do another one. This is a little more involved. So here we're doing a projection and extracting just these 3 fields. So for instance, we are ignoring the major ID, right? So we're only extracting these 3 fields, right? And let's see what transformations we could do, right, to the output. Right? So for instance, well, just like that, in the output, you would have 3 columns. The column would be SID, SName, and graduating year. Yes, right? But with the as keyword, I can rename the columns. So instead of SID, it would display as new SID, and graduating year column would actually be displayed as graduating decade. Okay, and this is a hint of where we're going, right? We're going to try and calculate a brand new SID based on the original, right? So for instance, what we could do as a new SID, maybe this is a new a new set of freshmen, right, that are coming in, and I have to calculate SIDs for them, right? So we're going to concatenate the old SID, right, where it might have been 1, 2, 3, 2, 3, 4, 4, 5, 6, whatever, right? We're going to concatenate in front of it the keyword or the string student, and then hash or student number. Okay. Notice the single quotes. We're going to concatenate that. So now the new SID column, right, it's going to be called new SID, and the values are going to be student number 1, 2, 3, student number 2, 3, 4, blah, 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 instead of just 1, 2, 3, 2, 3, 4, and whatnot. Yes. This is just an exercise, just showing you what you can do. For the graduating decade, right, the graduating year was just 2007, 2011, 2017, 2000, right? But we're going to calculate instead the graduating decade. So by decade means, if you graduated in 2005, then you graduated in the decade of 2010, right? Within the first decade, the second decade, the third decade. So the decade of 2010, 2020, 2030, 2040, right? So how can we do that? Well, we can calculate that by doing some integer manipulation. We can divide the graduating year by 10, so we're dropping the last digit basically, right? Then we're casting it to an integer so that we're dropping that decimal, right? And then we're going to multiply by 10 again, right? So 2005 becomes just 2000, right? 2012 becomes just 2010. Yes, right? So in that case, we're on the fly calculating this decade that you graduated, and the column is called graduating decade. So there they are, right? So Joey graduated in the decade of 2000s, whereas Art is going to graduate in the decades of the 2020s. Make sense? So let's do another one, fairly complex. You can, on the fly, have a little bit of if statements, right, or logic, where values, not only can you do arithmetic operations like we just did, not only can you do string operations like we just did, right, but you can have actual logic. As you are iterating and displaying the output, you can say, well, if this is true, then the value is this, right? And if that's true, then the value is that, right? Something like we've done maybe in Excel, right, where you have data, right, and then one of the columns you have a whole bunch of if statements, right? You might say, if the grade is greater than 94, you get an A, right? And if it's greater than 90, it's an A minus. If it's greater than 87, then it's a B plus, and so on and so forth, right? And so that field basically has a whole bunch of if statements, yes, right? Or you can do it with a whole bunch of switch case statements, right? And so and SQL supports that. You can say case, when the condition, then the result, right? And you can put all sorts of like nested if else, if else, if else, if else. Okay. So let's look at this really, really trivial example where you have a table that has a single field A that has values 1, 2, 3. Yes, very, very trivial. So we're gonna run this through a query like this one. We're gonna do a select A from test, just gives you this, right? Now we're creating a brand new field on the fly. We haven't given it a name. We didn't give it a name. We would use A as the keyword as, right, as something, but we didn't. Right, so it's gonna, by default, it takes the name case. Okay. So the second field here, so this red calculates each one of these values, saying if it's A, then return 1. If it's 2, then return 2. Otherwise, just return other. Right. So that's where the strings 1, 2, and other come in, right? Based on the values that we have here. See that? Right. So it's basically on the fly. You can make all these calculations. Something that you would expect that if you could do it in Excel, obviously you should be able to do it on SQL, right? There's a simpler version of this where instead of having here multiple predicates, right? If A is equal to 1, if A is equal to 2, these are all individual if else, if else, if else, if else, right? The simpler way to use just switch case, right? In switch, you only have one predicate, right? One expression that whose value is then compared against multiple cases, yes? Right? So the same thing here. You would say case expression, and then when value, when value, when value, when value. So that one expression gets compared against multiple values, and the one that's just the one that's the same, you have the results, right? The only difference in that in switch case, in most programming language, you need like a break, right, to break out of the case. Otherwise, it just has a fall through behavior. Not here, right? The one that's true, that's the only one that executes, right? So there's also, so here's an example. Let's use that. We can use that. Actually, no. Yeah. Where we might want to calculate the fact we want to calculate whether a student is a alumni or not, right? So for instance, we could do is take all the students, take all the fields of the student, right, and then add a new field called alumni, or how long has this person been an alumni, right? And we can do that by calculating their graduating year the current year minus their graduating year, right? And that could be positive if they graduated already, or it could be negative or 0 if they haven't graduated yet. Yes, right. So that last column called graduating years will be positive if you've graduated already, or will be negative or 0 if you're not graduated yet. Yes. Okay. So that output Q69, we can use that as an input into something, into another query. We use that as an input, which we don't know how to do this yet, right? But this is basically a view, right? We'll see later on that this is basically just a view, right? And so what we're doing here is that we're retrieving all the fields that we had before, but we want to have another column at the end called the status, your graduating status, right? That is either going to be alumni or whether you're still in school, right? And basically it's checking to see if the alumni years is positive, then you've graduated already, you're an alumni. Otherwise, if it's 0 or negative, then you're still in school. Make sense? So there's an example on using a query, right, that calculates the temporary results that I can use then as an input into a larger question, right? Where and typically that's what it entails when you want to ask complex questions, is that you will have multiple smaller questions that you build up into larger questions. Yes. Now some vendors support a much more terse, a less verbose version of the switch case, right? It's just a plain old if statement, right? If, right, this is true, then it returns the second argument. Otherwise, it returns the third argument, right? So if it's true, meaning you're taking the alumni year. If it's positive, it comes out to alumni, or not, it's in school. Okay, much more compact. Right, so let's talk about the from clause. Yeah, so up to this point, the from clause, we've been talking about single tables, right? Just a single table. It gets interesting when you start talking about multiple tables. That's when it's interesting, right? And so as it stands, just like that, that's a cross product, right? It's the it's a product that, is a product operation that we mentioned in relational algebra, right? That takes all the records, right, all the data points in one data set, and it combines them. It calculates all the combinations with the other data set, right? So for instance, in this case, we might have 9 students, and we have I don't know, 3 departments, right? So 9 times 3, that you'll have 27 possibilities, right? These 3 students, these 9 students with first department, these 9 students with the second department, and then these 9 students again with a third department, right? Now, being a cross product, you're considering all the possibilities, of which many of them make no sense, especially if one student is only able to enroll in a single department, right? Joe is enrolled in department 10. Why are we even considering Joe enrolled in department 20? Makes no sense, right? Nevertheless, that's basically what this would do, right? If you have employee against, if you have a one table against another table, by default, if you don't have a where clause, or if you don't have a join, then you are doing a cross product, right? Most cases, that's not what you want. Most cases, that's not what you want, right? Instead, most cases is you first do the product, but then you filter, right? You filter only the ones that make sense. I want Joe that is in the department number 10, not Joe in the department number 20, right? So I only want to keep the ones where I join, right, on some foreign key is equal to a primary key, right? So here's a predicate. I'm joining these two fields, meaning calculate the cross product, but only keep the ones where this is true. Make sense? Right? This means iterate over one of the tables as you are iterating over the other tables, right? So consider all the possibilities, but skip the ones that don't meet that criteria. Only keep the ones where the criteria is true. But you still have to consider all of them, right? You still have to consider every single possibility, right? So you're still going to have to compute the cross product. Now, this is such a common operation. This is such a common operation that we call it the natural join. It's what you would normally think, right? Of joining two tables. You know, it's like, duh, yeah, that's the only thing that I would ever do. But indeed, there are actually other ways of doing this, right? For doing other things, right? And those we don't call it we don't call it the natural join. We call it well, we don't call it the unnatural join, but we just call it either the left outer join or the left inner right outer join, and we'll see the full outer join. Yeah, so the natural way that we think about it is either called the natural join or the inner join. Okay, when you just do a plain old join. All right. So let's look at a simple join. Let's see. We have here 3 persons, and we have 5 orders. And the persons on the left hand on the top, that's the primary key, PID. Okay. Whereas down below the order, we have a foreign key also called PID. Right. And you'll notice that we have here 4 records whose PID refer to actual persons. Yes. But we have a foreign key who's referencing a non-person, doesn't exist there. So somehow this is breaking normal referential integrity, right? Somehow it's breaking referential integrity. The database would have not let me introduce here that data here. It would have stopped me. But nevertheless, I want to try to make a point. Yeah, so this record is a foreign key to a primary key that doesn't exist. Yes. Okay. Also notice that there's a person over there, right? That Dole, right, who doesn't have any orders. See that? So it's kind of like a mirror image here of things that are that occur here, have no mapping over there, and same thing, right? There's things that are happening on the other table have nothing to do with this table. Yes, but there's an overlap of records that do match, right? Match each other. So let's take a look at the natural join first. So the natural join is that you say join person P with orders O, where the foreign key of one is equal to the primary key of the other. Yes, this is what we would normally do. And there it is, right? You have the records of one of the tables from the person table with some of the fields from the other table, right? We join them, we fetch fields from two different tables, and then we collate it into a single one, right? And so this record comes from the orders, and these 2 comes from the person. Make sense? And notice that we don't have Dole, right? We don't have Dole here because Dole didn't have any orders, and we don't have the orphaned order here because there's no one there that matches. Make sense? So this is what we would expect. Now, would we expect anything else than this, right? Is there anything that you could possibly want other than just this? For instance, left join. So left join says, okay, I know there are records that are associated. Yes, well, give me those. But in addition to the ones that match, which are natural, yes, I also want the ones that don't match from the left table, right? Meaning, give me the ones that match from both tables, but in addition, give me the one from the table on my left of the join, right? So wherever the join is, from the left, so table 1. So if there are records on table 1 that don't match, I want them too. You want to say, well, why would you want that, right? So why would you want go fetch some data that has no equivalence in the other record? Why would you ever want that anyway? Okay. And there's another one, the right join. You could also say the right join, meaning If there are records that don't match, well, I want the records from table 2, even though, right, there might be records that have no equivalence. Why would you want to do that? Well, for instance, right, here's a case. If I have persons and order IDs and I do a left join, if they do a left join, notice that Bob Dole, even though they had no equivalence in the orders, they're being brought in, and it makes sense that there is no order ID for Bob Dole. Makes total sense. And you might ask, well, why do we even bring Bob Dole? You know, why would we ever want to have that? Or so, and here's one example on why would you want that, right? So imagine you are generating, you're gonna have a party, and you want to invite the staff, right, over to the party, and you want to invite their spouses, right? And so you might have 2 different tables, a table where it shows a list of all the staff, right? And you might have another table where you have all their spouses, yes? And you're writing up the invitations, you know, Mrs. and Mr. and Mrs. yada yada yada, please come, blah blah blah, come and join us this Christmas if Fauci lets us. And that, so, but not everybody's gonna have a spouse though, right? And so that means that when you're gonna join these 2 tables, if you only do a natural join, that means that you're only going to retrieve those folks that have a spouse. So what happens to all the folks that don't have a spouse? Are you not going to invite them? Right? It says, are they not invited? Only the ones that is Mr. and Mrs. What about if it's only a Mr. or a Miss? Right? And so you might want to invite them as well. So you might want to retrieve data that also is not part of the that has no equivalent. So in this case, right, if you know, if the question might be, you know, find the names of each one of the staff and their spouses, if any, right? Meaning, if there are no, I still want them anyway. You know, invite them anyway. So to be able to do this query, you would have, if you only do the inner join, you would only invite those that are married, right? And you'd be discriminating against folks that are not married. Yes. Yes. Yeah, if you don't say anything, it's the inner join. It's optional. Yeah, if you don't say inner join, it's understood to be inner join. Only if it's not inner join, you have to explicitly say left or right. Is there what? No, most cases is you want an inner join, right? And that's why it's a default, and you don't have to specify it. You know, only when it's not inner join, which is the rare case, right? Then you have to specify it. Yeah. Yeah. So because of that, if any, at the end of the sentence, right, we deduce that the inner join is not enough, right? That we need to add the left join in there. Okay. Right join is kind of the mirror image, right? And it's only relative to where the join keyword is, right? So depending on how is that you wrote the query at first, right, you might want to leave it later. We'll see later on when we talk about performance, the order of the joins can improve performance, where you might want to start with, you know, if you have multiple joins, you want to start with the first join that reduces the search space the most. Right, so that you make the biggest reduction first, right? So that the later searches are smaller, as opposed to doing a search that is very broad, and you know, and gives you the search space is still big, right? And you have to, and every time you do a join is a, you know, it's a square, you know, it's an exponential increase, right? So if you're doing, you know, 2 joins. If you're doing a join, that's quadratic. You know, if you're doing 2 joins, it's cubic, right? So the more you can reduce the search space as early as possible, the better, the more you're gonna, you know, bring down that curve, right? So yeah, so the order matters. So whether you chose, you know, table 1 or table 2 to be in that particular order, you might not have a choice to change the order, right? So you want to keep it right or left. So here's an example of doing a right join, right? So you're bringing the order that doesn't have the person associated with. And there's also full join. So full join meaning yes, find me everybody who has a match, but also retrieve for me all the ones that don't have a match, right? So for instance, you might have, first the ones that have a match, right? The first 4, and then bring all the records that don't have a match for the left-hand side, and then all the records that don't have a match for the right-hand side of the table. Okay. And then several joins, yes. Product, you're doing all the comparisons. So for instance, Garcia only came back with 2 records, right, that had the match, but it didn't come back. So Garcia was only came back with the records that it was matched against, whereas a cross product would have also brought Garcia also for Dole and for all the other records that had nothing to do with that, right? He had only retrieved the ones that matched against them. Yeah. So a full product would return, Boone with 77895, right? And Garcia with 22456, and Garcia with 24562, right? And or this with Boone, this with Garcia, this with Dole, right? So we don't want that. That's a cross product. Yes. So if it's one join, then it's quadratic. So every time you add another join, it goes up 1 order of magnitude. Right. So n squared. If you add another one, it's n cubed, n4, and so on and so forth. Which, if you've seen algorithms, there's a way around that, right? To use hashing, or doing B trees, or doing that can bring quadratic down to logarithmic, or even constant, right? And so we'll talk about that. That's why we do indices. Indices allow you to bring down that operations down to linear time, or at most logarithmic time, as opposed to quadratic or exponential. But if you don't have any indices and you don't have any B trees or anything like that, then yes, you just have straight up quadratic and exponential performance. Yeah. Right. So if you have, how are we doing with time? 10:48. Let's have a really quick break, like 5 minutes at most, and then we'll come back right after this. All right, let's continue. Can you hear me online?
Yep.
Okay.
Professor, just before we go on, I do have a question.
What's up?
Yeah. Do we still have class next weekend? Next week, because I believe it's a holiday on Monday, but I don't know
Oh, right.
if classes are exempt.
Oh, wow. Next week is a holiday. What holiday is next week?
I believe it was.
Oh, Columbus.
Yeah.
It's Columbus Day, right?
Yeah. One of those.
Oh, we still do those that holiday? I thought we stopped doing that.
I was just a bit confused just looking at the calendar, but
Yeah, no, I think you're right. Yeah, I think next week there's no classes. It's observed.
yeah,
Yeah, I'll make a post about it. Thank you.
no problem. Thank you.
All right, so let's keep going. So up to this point, we've been considering single joins, right? Meaning two tables joined, which typically means do a cross product and do a predicate. And if it's just a single join, then it's easy, right? You just say, student, table 1 join with table 2 on a particular predicate, right? Now you can do a 3-way join or 4 or so on and so forth, right? But every time you make a join, you can break it up into multiple 2-way joins, right? Where a first join is then the input, like the output of the first join is then the input of a second join, right? So here's the first join, right? That is then used as an input for the next join, where we are joining with the section K on a different predicate, right? Now, this is all well and good, and it's certainly you can write it in such a way that it's fairly easier to read. Nevertheless, it's often syntactically hard to parse this syntax. So we do have an alternative equivalent syntax, right? We call the implicit join, right? So where the normal syntax, where you use the join keyword, right, is referred to as an explicit join. So you're saying that, okay, I'm explicitly joining this table with this other table, right? And then here's the predicate, right, to filter it. So instead of that, you can use an equivalent syntax that you specify a cross product, right? So here's a cross product, but then the filter, right, where the join happens, right, is that in the where clause you specify which two fields are you filtering by, right? So the original join is written with the explicit keyword join, whereas in this one you don't have, the join keyword doesn't appear anywhere, right? You first specify the cross product between the tables that you want to join, right? And then you can have all the filtering that goes along with that, right? Same thing if you have another one, if you have 3 tables or 4 tables, right? And typically for every 2 tables, you should have at least one, right? One predicate that maps a foreign key of one with a predicate for the primary key of the other. Right? So in this case, we have 2 tables, we have 1 predicate. If you have 3 tables, typically you would have 2 predicates, right? One that would maps the foreign key to the primary key of the first 2, and the next one would map the primary key of one with the foreign key of the other, right? So it's kind of like navigating from primary key to foreign key, and then primary key to foreign key, right? And you would have you would have an and, right? So we have predicate and predicate, and so on and so forth. So if you miss one of the predicates, you'll produce a cross product, right? Notice if I don't have this, then I would have the cross product between these 2, right? But because I have this predicate, I'm filtering, right? I'm not doing a cross product. But if I have a 3rd table, and I don't have an additional predicate, then I would be doing a cross product of the results of this cross product with that additional table. So you have to be careful to count. Like for every you should have the number of tables minus 1 predicates, right? So that brings us to the where clause, right? Notice that the implicit join happens in the where clause, right? So let's visit a little bit what the where clause is, right? So yeah, so in the where clause, you have all sorts of column operators that allow you to establish the predicate that you want to do for filtering the records that you want, and the operators are written in terms of these Boolean operators, right? That allow you to compare fields. Yes. Here. Yeah. Oh no, in a join you can, right? Because you can use parentheses, and so it's explicit what you're doing, right? Whereas here, you know, the predicate of these two are implicitly provided here, right? So basically, you know, this is as if you were doing the parentheses, and this is where you're filtering the output of these two, right? If you have a third and you don't have a predicate, right? It would first calculate the subset of the cross product of this filtered by this predicate, right? And the result of that will be cross product with whatever new table you would have. So yeah, there's no explicit parentheses or order. Later on we'll see that all this is compiled into actual executable in steps. What the database does is that it parses your SQL and it generates a plan. And the plans look very much what the relational algebra we just saw. It's just a whole bunch of functions that are going to be called in a particular order, right? And you can see the flow of what's going to execute first, and that's how you can tweak the performance, right? Of saying, you know what, I'd rather do this before in a different order. It's faster if I do it this way or the other. You can see the plan that's going to execute, and so you'll see that the implicit parsing of this parses into the same thing that one parses into, right? In that order. I'm sorry? Yes. Yeah. Oh, yeah. Yes. 2 separate queries. Yes. Which I'm saying they're equivalent. Yeah. Yeah. So right, we use these Boolean operators that allow us to compare. I'm sorry, not Boolean operators, just arithmetic operators that allow us to compare values against each other, plus the between, like, and in that allows us to consider multi-value, you know, like arrays or things like that, right? So for instance, in this case, we're doing a really simple where city is Lowell. So we're just filtering from those 3 records. We end up with just these 2 records where the city is Lowell. You can use Boolean operators and, or, not, and parentheses, right? So that you can, you know, create all of complex Boolean operators with Boolean expressions with these operators, or, right, it allows you to, you know, whether one allows you to combine predicates, right, so that either one could be true, and that's, you know, allows you to filter that way. Or you can use parentheses to establish a particular order of operation. Now we had mentioned that if you had multiple joins, it's kind of awkward if you use the join keyword, right? It could get fairly complex. If it's a single join, that's fine, right? You should use just plain old join, right? But if you have multiple, then it can get you know, hard to read really, really quick. So imagine we already have a query like this where we filter, you know, students that meet a particular criteria. Yes. Now in this case, this is not a predicate that deals with foreign key, primary key, or anything like that. No joins here. Yes, this is just a normal non-key Boolean expression. Yes, your graduating year and so on and so forth. But you can combine them, right? If you have a join where you're joining, you know, the students with the enrollments, and then the enrollments then with the section, right? Then to implement that in an equivalent implicit join, you would have the cross product of all three, right? And then navigating from the primary key of the student to the foreign key of the enrollment, and then the foreign key of the enrollment to the primary key of the section, right? So we have three tables, so we need at least two key-based predicates, yes, that are doing the join. Now you can have both, though, a combination of predicates that deal with the joining combined with predicates that deal with the non-joining, right? Here, the ones in red are doing the navigation from one table to the other, right? Whereas these here are just plain old filtering, right? I just want the ones that meet this criteria, right? Now, these over here exist, we know, right? The foreign keys and primary key, we know that those exist because those are specific features of SQL, right? That's how SQL represents relationships between records, yes? Right, so usually these fields are, artificial fields, like social security numbers or student IDs, right? Those are artificial keys. They don't represent any physical reality in the world, phenomena. Whereas names and years, right? Those represent real things in the world, right? So you can combine both of them, right? All right, so let's look a look real quick on between. Between allows you to give a range, right, and filter out values that fall into any one of other values that fall into this range, and these can be either strings or can be integers, right? If it's a string, then it uses the lexicographical alphabetical order of the string to see if it fits into these two ranges. So here's an example of using strings where we're checking the last name is alphabetically between two sets of strings, right? So it comes back with Dan, if it's between Boone and Garcia. You can also use a not operator, right, to kind of calculate the inverse, right? The ones that don't match this criteria, right? Then you can use the in operator, where you can give it a vector, right, or a list of values by which your attribute or your property will be compared against, right? And so, for instance, you could say, well, this column name I'm going to compare to see if that value of that column is any one of those values in the vector, right? You have to be careful. This creates it's an expensive query, right? Because not only are you iterating over each record, now you're iterating over each value, in that record. So it could be very expensive, right? And you can get clustering and things like that. So yeah, in this case, we're checking the last name, and then we're going to iterate over this list of last names and see if it's in there, and it'll pattern match, see if it's listed in that list of last names, and then we'll return that one person. We mentioned earlier, right, allows you to do pattern matching, anything that starts with a J over here, right? Again, that's very expensive. Ideally, you would have a long string, right, at the beginning, right, and then use the percentage to compare maybe the ending of that string, right? That would allow you to quickly filter out, large portions of the query, right, and then only compare the last 2-3 characters. This current user, so you can current user is a global variable that is tied to whoever's logged in using the database currently, right? That's useful. For instance, if I can make a query based on my current user, I can list, give me all the sections for me, right? Whoever, and that would give me the sections that I'm teaching, right? Or the students that I'm advising this year or whatever, right? So, and if some other professor uses the same query, they'll get a different set of sections, right? A different set of students, but it's the same exact query, right? Where current user is the currently logged in user. Okay. All right, let's talk about subqueries. Yeah, so subqueries allow you to do small, use the results of previous queries, smaller queries presumably, right, and combine them into larger queries, right? Kind of like what we did earlier to do the calculation of what was the maximum number of A's in across all sections, right? We first identify the enrollments. We use that output to then group by the sections, and then we use that again to group by and do the count. Remember that, right? Where the output of one of the queries was then used as the input of another query. Okay. Well, let's see how you do that in SQL, right? So basically, what we're going to do is that we're going to have a select statement. And that select statement, the output of that select statement can then be used in a bigger select statement, okay? Now, that bigger select statement has different sections, right? It has the select clause, it has the from clause, and it has the where clause. And in each one of those three places, you can have a subset. You can have a subquery in the where clause, or a subquery in the from clause, or a subquery in the select clause, right? In each case, you have to be careful how you use it, right? So let's take a look at some of these, right? So first, let's look at using it in the where clause. This is where you mostly use select subqueries, right? So for instance, you have a bigger select statement in the black, and then you have a smaller select statement inside in a parentheses, right? Used right in the where clause. See that? So notice that we have the select clause, select yada yada yada, where blah blah blah, right? And then we have where so and so field is in, right? Whatever this comes back with, right? Now that in, the keyword in, should give us a hint on what that inner select statement should do, right? If you remember, the in keyword says that you're going to compare a field with a vector of values, right? You're going to iterate and you're going to check if that value is any one of those values that are in the vector. Yes. Okay. So that means that this select statement, this inner select statement, better return an array of multiple values, right? Of single scalars. So it's a tuple of multiple values, but it can't be a tuple of tuples, right? It can't be a vector, right, where each value is multivariable, right? So it can be an array of integers, an array of strings, but it can't be an array of arrays, okay? It has to be an array of literals, okay, of single values, where then the in can then iterate and compare the field with those scalars. Make sense? Okay. Now, what if that instead said table1 dot field equals, or is greater than, or is less than? Well, that means that the select statement can't be an array. It has to be a single value, right? If you say age is greater than, well, then you have to give me a number, right? You can't give me a string, right? It has to be a number. Right? So again, depending on the operator here, right, the inner select statement better calculates whatever the outer operator is expecting, right? The in is expecting an array. If it's a comparison with some numerical value, well, this select statement better return a single numerical value. Or if it's a string, then this better return a single string. Make sense? Right? In this case, well, let's actually see some examples. So let's see an example where we have a query where that I run every semester for the deans, the students that made the dean list, right? And I know it's Alice, Bob, and Charlie, right? And I always have to retrieve their information, because I don't know, I have to invite their parents or whatever, I don't know. So yeah, so I have a select statement that retrieves the student details where the first name is Alice, Bob, and Charlie. But every semester this changes, right? And so I might want to establish a criteria by which I select these three folks. Okay, instead of me hard coding this list and calculating in my head and making the list every semester, I can very much formally establish the criteria by which this is a list, and I can generate this list dynamically, right? So I established that query, and my formal query is that, oh, only students that in the science, right? And that gives me my list of students. So I would say, select first name from student details where the subject is science, right? And that gives me the list of the students, yes? Right, notice that the list of the student has to be, I'm expecting a first name, so I'm gonna be comparing presumably with values of the first name, right? I can't be returning anything else, not last name, right? And especially not two fields, right? Because the in expects an array of single values, right? If I return first name and last name, then I can't compare a single string against an array of things, an array of arrays, okay? So yeah, so I have to make sure that, that this returns what my outer select segment is expecting. Right, so here's another example. We're giving some statistics on GDP and population and area about multiple countries in the world. And somebody's asking me, okay, well, give me all the countries whose population is larger than Russia. Okay, well, those are two questions. Those are two different questions, right? One of them, I need to first find out, what is the population of Russia, right? And then the outer question is that, okay, well, now I have to iterate over all the countries, get their population, and see if I then compare it against the population of Russia, right? So those are two questions, and typically that involves writing 2 or 3 or 4 different queries, right? So the inner one says, okay, well, now first I have to find out the population of Russia, right? So that's the inner question. You select population of from the GDP table where the name is Russia. So that gives me a single value. That's perfect because that's exactly what I'm comparing against, right? This greater than is expecting a single numerical value, right? And presumably population is coming back as a numerical value. Yes. Yep. This one? This one. So you could flatten out, and there's just like you have functions within functions within functions, you could flatten that out into a single bigger function, right? And whereas what we want to be able to do is have dedicated queries, right? That you can then reuse. And so this eventually will have a name. These subqueries will have a name that you can then reuse as if it were a table or a function that you can call it eventually. But yes, you could flatten out anything that is hierarchical into something that is just flat, right? So yeah, we could convert this into a single query. Yep. But I'm trying to make the point that it's easier to first break up a bigger question into smaller question that can then be combined into a bigger one. But yes, you absolutely can flatten. There's an equivalence. I think it's more or less the same, the kind of same question when you're doing software engineering in general, of finding your reusability, should I break this class into multiple classes or should it be one big class, right? And or a function, right? Should I break up this big function into smaller functions? It's more it's when you identify that you are copying and pasting the same algorithm, and that gives you a hint that says, wait a minute, can I just put this into a function that I can then parameterize it, pass a parameter, and then it gives me back that. And that's where we're going. What we want to be able to identify says, hey, finding out the population of blah, 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 whatever, right? That's actually something that I keep using. Ooh, let me make a view out of it, right? And then forget about it, right? And then I have that view that I can just reuse as if it were a table for me. Yeah. But yeah, it's the same questions you have of software engineering, of either going top down or bottom up, right? Where you break up some big problem into 2 smaller ones and then you break them up again, or you do a bottom up. You start, I create lots and lots of little things that are small Legos that I can build on top of each other, right? So it depends. Oftentimes it's a little bit of both, where you do a little bit of bottom up, a little top down, and you meet somewhere in the middle, right? And it's just software engineering of breaking up large things into smaller ones. Yeah. So once we've calculated the population of Russia, we can, this comes back with a single scalar value that I can then use as that I can then calculate against the population. Yeah, like the example I saw earlier, right? That we use in, I think there were 2 AND operators, right? And we broke it up instead of having one single AND operator, we broke it into 2, one nested instead of the other. Right, and one of it's more easy to understand as a flow of data, right, and how it flows and how it gets filtered, as opposed to the other one is a single query with a complex query, a complex Boolean expression. Okay, so that's using the select statement in the where clause. Yes, right. And again, we have to be careful. It's either a vector or a single value. You can also use the select statement as in the from clause, right? So in the from clause, if you remember, we're always expecting a table or something that looks like a table, right? So in here we have the from clause has the first table is suppliers. See that? And suppliers might have a whole bunch of fields, it might have a bunch of records, yes, right? And then it says comma. So the first table is suppliers, comma, followed by something that has to look like a table, okay? And that table is this parentheses here that starts off with this select, closes here, and then we're giving it a name. See that name. So this name is the name of something that looks like a table, or that must look like a table, right? That's because that's what from is expecting, a table, okay? And we're giving a name, right? So how we're calculating, so the code here in red is generating something that looks like a table. It's gonna have a whole bunch of fields, it's gonna have a bunch of records, right? Which fields? Well, it looks like the fields are what? The field is supplier ID, that's one of the fields, comma, and then another field called total amount, right? So those are the 2 fields in the table that this inner select is generating. Okay, those are the fields. What about the records? Which records? Oh, well, the records, right, that are calculated by looking at the orders table, right, grouping by the supplier ID, right? And so it's going to generate the aggregation of all the sums of the orders, right, for grouped by the supplier ID. Right, so there's going to be a whole bunch of supplier IDs, and then the sum, right, of the amounts. Yes. Okay. So internally, this is going to have a whole bunch of aggregations: the supplier ID and 2 fields, right? The total and the supplier ID, and a whole bunch of records. And that is going to be referred to as a subquery. That's it. So 2 tables. Now this is going to calculate the cross product between these 2 tables. The cross product, but we don't want all of them. We don't want all the records, all the combinations. We only want to keep the ones where the supplier ID, right, this supplier ID, right, which is of this table, matches the supplier ID of the suppliers table, right? So we're doing a pattern match. We're filtering only the ones where the records on the inner table matches the suppliers in the outer table, okay? So we're doing a filter here. Okay, and one of them is referencing a field in the inner table, and the other one is referencing the field on the suppliers table. So notice that we were displaying fields from the suppliers table, the name, and then the total amount that was calculated inside of the inner select statement. See that? Right. So again, this is an inner select statement. Again, later on we'll use views to make this read much easier, right? If this indeed turns out to be a query we keep using over and over and over, right? Well, why not just give it a name, right? And call it, order by supplier or something, right? And we can create a view, and now this would be treated as if it were a table, a real table. Okay. So here's another one. We are doing another select, counting the number of columns, doing some subquery, and then retrieving some fields from one table and some fields from the other table. Union is operating on, again, 2 tables. And basically, we want to be able to grab the values or the result set from one query and concatenate them with the result set from another query, right? So you might have, one query and another query, right? And one of them calculates, 30 records, and the other one calculates, 200 records. And you want to just stick them together as if it were one single result, right? With 230 records or results, right? The problem here is that we have to make sure, right, that they are compatible, that the results of one query is compatible with the results of some other query, right? It makes no sense if one of them is calculating a whole bunch of dates and the other one is calculating a whole bunch of salaries, right? And they don't match. So how do I put them together? How do you concatenate them, right, when there's no match whatsoever? Right, so here's a simple example. You have two tables, right? Although the matching here is pretty simple. They both have IDs. They both have names of employees. The only difference is that in one table, the column is called ename and the other one is called emp name, right? But the data types, other than that, the data types are the same, right? So if I do a query on one of the tables and it comes back with an ID and the enames, and I do another query from the other table, right, and comes back with IDs and emp name, if I want to concatenate them and unite them, doing a union, I need to somehow tell them that, hey, even though this is called ename in this query, yes, and over there it's called emp name, I need to somehow say they're the same thing, put them in the same column in the resulting union. Okay, well, that's easy. That's especially if the data types are the same, right? If they're not the same, well, I'll need to be able to either do a casting of one of the fields, right? Maybe I'll have to do a rename of the field. Okay, in this case, we can get away with just renaming the field, right? So for instance, if I do a select employees from Canada and it comes back with ename, I want to do the union with the employees from United States. Well, at least I'll have to rename the field to match the one from Canada, and that'll be ename. Now, if they were not strings, somehow they were some integers or whatever, I'll need to cast the integers to make them into the correct data type that it's expecting, right? So if one was string, then I'll need to cast those integers into strings, or vice versa, right? I'll need to finagle. Right now, we can just get away with just renaming the field so that the two fields match. In that case, right, you end up with just one output of ename, right? Now, notice that I'm with the employees from Canada and the employees from USA. Notice that I'm bolding Dole here, right? Stephen Dole. And the reason I bolded him was because Dole appears in both tables, right? So at some point, Dole worked in Canada, worked also in USA. So they appear in both databases, right? Now the default behavior is that union identifies any duplicities, right? It finds that, and if it sees that the same information is in one of the results as the other one, it'll skip over it, right? It's smart enough to say, oh, I'm not gonna, if you're gonna union this, right? It makes no sense to have it in both places at the same, both, you don't want both of them. But you might want both of them, right? So you would have to explicitly say that you do want both of them, right? With union all, right? So then it'll bring data from both of them, even if you have duplicates, right? So order by, as I mentioned earlier, it doesn't actually sort the data, right? Instead, it makes sense. Once it extracts the data, it will order it for you for your visual consumption, right? That you might want to sort it by last name or by order by date, order by some criteria. Now, by default, it orders by ascending order, right? If it's a number, it's just the by order of increasing number. If it's a characters or strings, it's by lexicographical alphabetical order. Okay, so the syntax is to have order by, and then the field or fields. You have multiple fields, right? Column 1, comma, column 2, comma, and by default they're ascending. If you want a descending, you have to explicitly put descending. So here's ordered by last name, right? So when it spits it out, it doesn't actually reorder the table. The table stays the same. You should never assume that the table is ordered in any particular way. Okay. Only when you start talking about primary keys and indices, right? Then you can start thinking about that an index might be ordered in a particular way, right? For performance reasons. Then you can start thinking about, oh, well, if it's indexed by last name, that it must be that the index is ordered by last name, right? So that you can use performance enhancements like binary search or trees and things like that to improve performance. But other than that, you should not assume that tables in any way are ordered in any way. Yeah, so here we're ordering last name descending. Right, let's talk about self-joins. So self-joins, if you remember, we had mentioned that in some structures you want to be able to represent hierarchical order, right? Where in the same table you might have records that are related to one another by having a foreign key in one table refer to a primary key in the same table, right? And this would allow you to implement hierarchies such as, say it's an employee table, and then everybody in that table is an employee. But nevertheless, there's not all employees are the same, right? We all report to somebody, right? So there is a hierarchy where 10 of us might report to a manager, and 10 of those managers report to their managers, all the way up the chain, right? Up until you get to the CEO and whatever, right? And they report to the board of directors. So to do that, you can have things such as a primary key ID, and then you have a foreign key parent ID who points to who my parent is, right? So we call this a self-referencing data structure, okay? That allows you to implement recursive or hierarchical data structures, okay? Where you might have categories of DVDs and Blu-rays, right? Under the category, the subcategory movies, and PCs under electronics, but both, right, have parent or have the top. The top category usually maybe having the parent is null, meaning they're the root category, right? They don't have any parent, right? But all the other ones do have a parent. Yes. So how do you do queries that are self-referencing? How do you do that? Right? So the way you might want to do that is that typically, if you have two tables and you want to say that the foreign key of this table is equal to the primary key of some other table, you would say, table 1 primary key is equal to table 2 foreign key. Yes. Well, what happens if the foreign key and the primary key live in the same table, right? In your from clause, you would say table 1 and then table 1 again, right? You're not going to another table. You're staying in the same table, right? So to be able to achieve this, you have to rename the tables, or at least one of them. Okay. So for instance, it's the same table categories, right? Right, where you have subcategories pointing to parent categories and so on and so forth. So you're matching records in a category table, referencing foreign keys of categories in the same table. Yes. So you have to name them. So categories child and categories parents. See that? So here's where rename is crucial. Without renaming, you cannot do this. You have to rename them. And now you can say, okay, well, now you can say that the foreign key of the child is equal to the primary key of the parent. Okay. Okay. So this one is filtering out, right? Everybody whose the name is movies, right? Okay. Portable enums that I mentioned earlier, right? That in SQL, MySQL, enum is a keyword, right? That is supported by this particular vendor, but it's not necessarily supported by all vendors, right? So you to implement enumerations like this, where you might have a movie with a genre, you have comedy, drama, and horror, to implement it in a portable way, right? That you're not tied down to a specific vendor, right? You would implement it by creating a specific table that lists all the possible values as a primary key, right? And then the table that wants to constrain the value of a field can declare that as a foreign key that references this particular genre enumerations, right? And that way, the only values that genre can take now is only the ones from that genre table. Make sense? All right. Okay, let's talk about views. Yeah, so as I mentioned earlier, we might have subqueries, right? That up to this point, we've been talking about a query that might contain another query, right? And we call those subqueries, especially if in the from clause, right? If in the from, nested in the from, we call them inline views, right? And the reason we call them inline views is because we're now going to see what a view is, right? A better way of nesting these queries is to actually, especially if you see that it's happening, or you use just like you see an algorithm, right? A particular algorithm that you're copying and pasting all everywhere. That's an immediate flag that says, "Ooh, maybe I should put this in a function, right? I should parameterize it, and then I can call it and use it anytime I want." Yes. Right. So same thing here. If you find yourself that using a subquery over and over and over and copy and pasting everywhere, ooh, maybe I should wrap this into some abstraction, right? And then I can use it, give it a name, a good name, and then I can reuse that. So we've been hinting at this already with having a like left side, right hand side, assigning the results of a select statement equal, right? Assigning it to a variable, right? Q1, Q2. You've seen those examples I've seen, right? Q20, Q30. Well, the syntax to do that is to use the statement create view. Okay, so create view allows you to take a query that you find very useful, okay, and now give it a name, right? So this is how you would do it. You say create view, you give it a name as, and then the actual select statement, right? Use a select statement. Now, instead of using the select statement copying everywhere or using it under, in a parentheses, now it has a name. Now it has a name that I can reuse. Okay. And now I can treat it as if it were a table, but it's not. Right? You can treat it as if it were a table, but it's not really a table. A table is backed by actual records stored in the file. Right? Whereas this, even though I can treat it syntactically as if it were a table, it's actually when you invoke it, when you use it, when you use the name of the view, it just reruns the select statement again, right? Regenerating that intermediate table, right? Temporarily, so that you can reuse it in whatever context you want. Yes, right? Once it's used, it gets thrown away. Right. So every time you do the query, every time you refer to the view, it reruns the select statement. Okay. So here's an example where you create a current product list, right, where you have a select statement that retrieves the product IDs, the product names from the products table, where discontinued flag is false, meaning it hasn't been discontinued. Right? I might have hundreds of thousands of products, of which I only really have 10,000 that are not discontinued. Everything else has been just, falling away, right? And so I now have a subset. So now I have a current product list table, okay, that only lists a subset of the tables that are current, right, that are not discontinued. Now I can treat this table, it's not a real table, but as wherever I can have a table, use a table, I can now use this this query. Notice that I deliberately put spaces in there, right? This is not a real table, okay? But you can still use it. if you put quotes around it, right? It's a virtual table. It's as if it were an actual table. But we'll see the limitations though of this idea of this being a table, which is not a table, but you can treat it as a table almost. We'll see the limitations. So wherever you can use a table, you can use a view, right? So here's another query where I'm creating a products above average price, right? And internally, I can have a nesting of select statements that contain nested select statements that can use other views. So views written in terms of other views, right? Within nested queries, I can be as complex as I want. So this one is doing a select product name, unit price from the products where unit price, right? I'm doing an average. So I'm calculating an average. I believe I asked you to do this in the current assignment. We calculate an average, right? And then filter out the records that meet that average. Okay. And then they're collected into this bigger products above average price, right? Here's another one, create a view where the category is sales for 1997. And this is a view that is written as in terms of select statement, where the from uses another view. So it's a view written in terms of views, right? So the idea is that you would start creating smaller views, right? And then you can create ever more complex views, just like you would create a function, small functions, and then those functions you combine to write even more complex functions, right? So it's a mechanism that most languages have, which is ways of abstracting, right? Creating abstractions, right? And programming languages are, have lots of ways of creating abstractions, functions being the simplest way, right? Where you have a function written in terms of other functions written in terms of other functions. Classes is another way of creating abstractions, right? Where now classes are collections of functions, right? And variables, right? And then you have inheritance, and those are all different mechanisms that programming languages uses the idea of abstraction, right? Of creating layers. Humans are basically that. We're abstraction machine, right? So we've been using views all along, right? Wherever you've seen this Q65, Q13, Q whatever, all these examples that we've been looking at for the last couple of weeks, right? They just have been views all along, right? So this, before we had, Q65 was equal to select S name, graduating year from student. Now we can actually create one. You can say, create view Q65 as, and then the query, okay? And we've seen that you've already seen lots of examples where, we've been assigning results to Q variables, and then using those Q variables to then write even more complex select statements, right? Right. So those have been examples of queries within queries within queries, right? So we're using queries. Yeah. So this query, right, of using Q65 is the equivalent of, literally putting the select statement in there, right? You should never think of it as it being an actual table, even though it might have a fancy name and whatnot, right? It's not a real table, right? It's literally rerunning that query every time you refer to that view, okay? Now, so so views are very, very important for generating abstractions that might be useful for folks that are not technical, right? That are not data analysts. It's not us who are dealing with the database day to day, right? That we've made an effort to create a normalized table, right? We've broken up the database into these 5, 6, 7, 10 tables, but for the folks that don't really care about normalization, which usually are the clients or customers, right? They don't, they might find it inconvenient having to join this table with that other table, do a 3-way join, a 4-way join to extract the data. They would want everything in one single nice spreadsheet. Yes? Well, views allow you to do that. Views allow you to provide non-normalized data, right? That might be convenient for consumption without actually having a denormalized schema, right? So typically what we do is that we make every effort to normalize the schema, make sure that it has no redundancies, no nothing, but then provide denormalized views, okay, for the convenience of our clients, right? So if it's a registrar's office, right, they might find it inconvenient every semester to have to join the grades from the students from one table to the enrollments and then another table and the sections over there and the courses over there, right? And doing a four-way join to generate the dean's list for this year, right? Or whatever, right? So instead, what we do is that, okay, well, I'll create a view, yes, that extracts the data from the multiple tables, puts it in a nice view. It's denormalized because it's bringing in all this data that I made a lot of effort to break it up, right? But for your convenience, I'm bringing it up without actually ruining my schema, right? But I'm giving you a nice denormalized view. Make sense? Just for your, and oftentimes we call this external schemas. Schemas for folks who don't really care about the schema, right? So for instance, the dean's office might want the student info. They would want a schema that combines the numbers of courses that they passed, the numbers that they failed, their GPA, student name, right? Or they might want about the courses and the students. They might want a denormalized schema that has information about the courses and the students, which we made an effort to break it up, right? But they would want it to be denormalized. So we can certainly create a view that does all that query, that goes out to the enrollments table, to the section table, to the course table, and joins everything into one denormalized view for your consumption, okay? And it's convenient for them. Now, remember I mentioned that views, they feel like if they were tables because you can query against them, right? You can do select statements against them. You can use them anywhere with a from clause, right? Wherever you can put a table, you can use it. But it has limitations, right? For instance, in a real table, not only can you do a select statement, but you can also do an update, right? You can update the data, you can delete the data, you can insert new records into that data, yes? But what would it mean to insert or update a view? What would that mean, right? Because remember, a view is not a real table. A view is a collation, right, between multiple tables, right, and giving you a virtual record. That record doesn't really exist, right? The two of the fields in that record, quote unquote record, come from table 1, and three fields come from table 2, and some other fields come from table 4. Make sense? So inserting into the view would really mean inserting into multiple tables, right? Or if you delete the quote unquote record, I mean, what would that translate to? That would mean deleting 3 or 4 records in the original tables. Is that what it means? So there are limitations of what you can use views for, right? They're not real tables. Okay, so what does it mean? Well, if the database can uniquely identify, right, and do a mapping between a record in the view, right? If it can map it directly to the original records that were used, then yes, the database can do a few things, right? If it can determine that unambiguously that this virtual record matches exactly this other record, and only that record, yes, a delete on the virtual record should be able to be translated to an unambiguously delete in the original record. That makes sense, right? But if instead the record is perhaps a group or an average or a max or a grouping of multiple records, then that makes no sense. What am I going to, if I delete this record, that means I'm going to delete 10 other records. that were grouped into this one single record, that makes no sense. Yes. So if the database can uniquely identify a mapping between the virtual record and the original record, then yes, it can cascade operations on the view and cascade them to from the source records. Yes. So yeah, so if you have multi-tables, then no, you can't. If they're grouped, you can't, right? But if there's a one-to-one uniquely correspondence, then yes, you can operate it. So let's just consider. Let's say we have two tables, from the student table and the department table. We're extracting student information, department information into a view. Yes, right. So from the department names, from the department, we're retrieving the department name. And from the student, we're retrieving the student names, right? And we're creating a new view that has both the department and the name. Now, what would it mean if I delete Sue and she's in the math department? What does that mean? Well, how should that be translated? Does it mean that I remove the student record? Is that what I'm doing? Does it mean that I'm removing the math department record? Right? So you understand the ambiguity of what is it that you, how could this be interpreted? Okay. And so the most intuitive things that we might say is that, oh, if you delete Sue math, probably what you mean is that you're trying to remove the record for the student. Maybe that's what you meant, right? But probably you didn't mean to actually remove the math department. Okay. I'll say you change Sue's major ID, right? That she's now not in the math department, but now she's in computer science, right? So what does that mean? Are you changing the ID of the math department, or are you changing the reference for Sue to be the computer science department? Is that so? This is not a trivial. What is it that you want to do? Or if you insert Joe and drama, right, into this database, right, into this view, and we already have Joe and Art, right? What does that mean? Do you mean that Joe is no longer in the art department now? He's in the drama department. Is that what you mean? That we need to change the foreign key to point to a different department? Is that what you mean? Right. So notice that there is ambiguity on what is that you mean. What is the heuristic? What is the semantics of what you mean by inserts, updates, and deletes? Right. So that's where store procedures come in. Right. That you might want to be able to programmatically, right, capture updates, deletes, inserts, right, into certain data structures, and specifically and exactly tell what to do, right? So that if you say delete Joe from the drama department, I can detect that. I can trigger a function that runs a procedure that says, oh, I know what that means. It means that I am removing the Joe record, okay? So that's where stored procedures and functional programming comes in, that allows you to specify exactly what to happen, right? And that's what we're going to be talking about. Is that next week? I think that the week after that. All right, I do want to cover the assignment before we leave. Okay, so for the current assignment, what we're going to do is that I'm going to give you a database, right, that implements the relational schema that we discussed last week, right? So I guess the schema that I'm giving you is the answer to last week's assignment. And it's available right here. You can download it from GitHub, and you can import it into your database, right? And it provides several tables, right? One table for the replies, logs, ratings, posts, and users, okay? And it has values. Let me show you. I think I have it here. Okay, these are the tables, and you can, there's a couple blogs for Everyday Astronaut, SpaceX, Tesla, Hyperchange. You have a couple of users, Alice, Bob, Tim, Elon, Charlie, and Daniel. You have a couple blogs, we had a couple posts, I think, just a couple posts. So anyway, you're being asked to do a couple queries, right? Some really easy ones at first, like for instance, just retrieving all the users, right? So select star from users. Also notice that before every query, you are required to provide a comment. And comments in SQL start with a double dash, space, you need the space, right? And then the text, okay? Now the comment needs to explain what is the intent of this query, all right? Don't tell me, oh, I'm taking the foreign key of this with the primary key of that, and try to explain what the, try to explain with just in plain English, right? What is the intention? What answer are you trying to what question are you trying to answer with this query? Okay, very high level. So and like all assignments, I first give you an example and then ask you to write one on your own, right? So for instance, I give you this one, and then I ask you to do the same thing for the blogs. Yes. All these queries have to be done in a single file, right? And in the file, you're going to save it as querying relational databases SQL, and that's going to be part of your deliverable, right? So the second one is retrieving a record by its primary key, right? So here I'm returning a blog whose primary key is 2. And then I ask you to do the same thing for the posts, but for ID 1. Really, really easy. Again, everything should have a query, a comment. Then just use a predicate, like select all the users whose username is Elon Musk, and then I ask you to do the same thing for blogs whose name is SpaceX. Okay. Then I ask you to do a simple join between two tables. Using the join keyword between tables users and blogs on the user foreign key going to a primary key. And then I ask you to do the same thing, but joining two other tables on your own, okay? So this is using the explicit join syntax, right? So then I ask you to do the same exact thing, but using an implicit join, right? Where you don't use the join keyword, but instead you move the predicate down to the where clause. Yes. Okay. So all these implicit joins have been obviously on key fields, right? Primary key with a foreign key. But then I ask you to combine key queries, right? Primary key, foreign key, mixed in with non-key fields such as usernames and whatnot. Right, so now if you try it, and you're going to do it for blogs and posts for the blog's name, who is Everyday Astronaut. I then ask you to do a three-way join with users, blogs, and posts. Right, that because you have 3 tables, now you're gonna need at least two key-based predicates. Right, so that allows you to navigate between user blogs and then blogs and posts. Right? Then I ask you to do it on your own. Okay, later I ask you to do an aggregate, right, with a group by, where you calculate the total number of ratings, the likes for a blog post. You want to count how many likes a particular post has. I think if you look at the ratings, it has there are just 2 posts, post 1 and 2. So post 1 and post 2, and each post has lots of likes and dislikes. And so post 1 has 3 likes and 1 dislike, and post 2 has 4 likes and 3 dislikes. So I do that one for you. Count the number of likes. So count how many. So add them up, or add the number of likes. I guess I could use count. Actually, no, count no, because you have zeros, right? You need to sum up the ones. Whereas and then I ask you to do calculate the average score for the posts. So you're going to use these guys, the score. So there's some posts that don't have likes and dislikes. Instead, they have a score from 0 to 5, right? So you can do the average for post number 1. So you can just basically it's just the average of 3, 4, 5, and 5, right? Using the AVG aggregate function. So I'm using the sum aggregate function. You're going to use average aggregate function, right? Same thing for the other posts. So basically the average per post. And then I ask you to do an inline view where you use this query you did earlier, right? The query that you did earlier as an interview. I'm sorry, as an inline view for an outer question of saying, retrieve the blog's name, post, and total likes per post, right? Which is it's using the inner query to answer the outer query. Right? So I give you that one, and then I ask you to do the same thing with your own inline, right? But with the posts and the averages you did earlier, right? So the query that you did for this one, for this average, you can use that, right, as an inline view, right, for answering this other question. All right, so that one is that's pretty simple. Yeah, I mean, I give you most of everything, right? So the challenge here is you're gonna do this on, just on your own, right? Looking at the previous assignment. So in the previous assignment, you were given this class diagram. So we're given this class diagram, right, where you have a mapping between employees and projects and a mapping between projects and tasks. Yes. So given this class diagram, answer the following queries. What is the full name? What is the full name of the employee whose primary key is 1, 2, 3? Well, that's easy, right? It'll just be, select star from employee where whatever primary key you used. Some of them used employee ID, some of them use ID. Whatever primary key you chose, is equal to 1, 2, 3, right? So that's easy. Then what are the names of the projects assigned to an employee whose primary key is 2, 3, 4? So that's basically a join between employee, project assigned, and project. Right? You join these 3 tables so you can retrieve the name of the project, right, whose employee ID is 2, 3, 4. So you have to join these 3. Right? So where the primary key is employee is equal to the foreign key of the project assignment, and the foreign key of the project assignment to the project is equal to the primary key of the project. Yes? Right, so it's a 3-way join between the 3. Yes? So that's easy. So it says, what are the names of the tasks assigned to an employee whose primary key is 3, 4, 5, and project primary key is 4, 5, 6. So that's a 4-way join between employee, project assignment, project, and task. Right, following the foreign key of task to project, the primary key of project to foreign key and project assignment, foreign key of project assignment to the primary key of the employee. Right, so you need 3 key-based predicates, right, joining a 4-way product between these 4 tables, right, where the project ID is given to you and the employee ID is given to you. Yes, right. So we give you the project, the primary key of the project and the primary key of the user, of the employee, and the. Then it says how many projects is each employee assigned to. Right. So we're going to count how many of these grouped by employee. Right. So we group by. So you're going to create a bucket for every employee. Right, and you're going to put the projects in one of those buckets, right? And then you're going to just count how many project IDs there are. Then how many tasks does each employee have? So now you're counting this, same thing, group by employee, but you're creating all the tasks for each one of the employees. which basically is the same queries you did before. You already did that. You already did the joins before, right? So you could use those joins, right? Those previous queries as inlines, right? For this count, right? Because one of them gives you projects by employee, and the other one gives you tasks by employee, right? And that could be the inline query for an outer one. I don't ask you to do a view. I don't ask you to do a view, but you could do a view, right, to simplify this. Then same question, what are the average numbers of tasks? So this is the same question as before, but instead of counting the number of tasks, is the number of average. What is the average number of tasks per employee across all projects? Right, and finally, which employees have more tasks assigned to them than the average number of tasks per employee? So first, the average of tasks across all employees, and then the average by employee, see which one is bigger, right? So you have an inner one that calculates the average across all employees, and that is using the where clause, right, of the average of the by employee. Anyway, save that into a query file called challenge db4 fa21, and that's part of your deliverable as well. Okay. All right, excellent. Any questions? Yes. No, the ID of the employee, the group by the employee. If you know, I haven't given you any data. If it helps to create some dummy data, just to try out your queries, definitely, yeah, you should do that. Although you should be able to write it without data. Okay. All right. Any questions online? All right. Excellent. Thank you.